Okay, we'll get started on the space news, covering roughly the last month since our last meeting. First of all, just a brief update on DART, which was our planetary defense test. We talked about that every other time. It's just been a little bit of quantitative information coming back on that. Some stuff on the International Space Station, a few problems they've had, and some other miscellaneous news. We'll spend a lot more time actually on the Blue Origin making kind of a surprise announcement about making solar panels on the moon. They're saying they have the ability, and we'll talk about that and some other related lunar mining. And then something about recent launches to space. So the DART update. Those of you who have been to this before have seen this picture. DART is a spacecraft that smashed into the asteroid, the one on the right there, the small one. And the idea was, see if you can divert an asteroid by smashing into it. And sure enough, of course it did, and everybody probably has heard all that. But we got back some more information from some papers published in Nature earlier this month. They decided that it ended up ejecting about 1 million kilograms of rock out of Dimorphos, the small asteroid there. Now that sounds like a lot. It is a lot. Of course, that's out of a 4.3 billion, but still it was enough to make a significant dent in its orbit. And the other thing is it formed a tail, and that's shown kind of up in the upper right-hand picture. This is a kind of an aggregate picture here. It looks more like that. It looks a lot like a comet now. And it turns out that not everything with a tail is actually a comet. They've wondered before how these things got started, and apparently there have been a few other asteroids that had collisions like this, because there are a few asteroids that have tails like that. They calculated that the recoil from the ejected material probably increased the effectiveness of the DART craft by about a factor of 4. Meaning you got two things crashing together. You transfer the momentum of the fast-moving small ship to the large asteroid, but then because you also eject a bunch of material, that shoots out in opposite directions, that actually adds some additional kick just by conservation of momentum. So you end up getting about 4 times the effect. So that was
really a surprise for a lot.
It was. Well, there was a hope, but that was actually better than they were hoping for. So it was a good thing. So that was the good news there. So yeah, in this picture, there's a DART spacecraft on the lower left, the 2 asteroids, and then of course the asteroid with the tail there at the very end. Okay, some issues on the International Space Station. We talked last time about how the Soyuz spacecraft, which is the Russian ship that delivers crew to the space station, they had a coolant leak, and it was quite dramatic. There you could see little crystals of ice or whatever coming out of it. They concluded it probably was caused by a meteorite, which is what they had said. But what they did was they sent up a backup craft, meaning you send one up uncrewed. It's still there. I'll blow this picture up a little bit here. So the Soyuz craft, there's mission number 23 is the one that just arrived. The old one is still there. That is the one that's not quite good. What had happened was, since it lost coolant, now it can't control temperature very well, there was really concern you couldn't put people in that. They're still going to take trash and some other stuff back. They're going to attempt to go back. The real danger is, will their navigation computer still work, or will it get so overheated? So they're not going to put anything too valuable in that, but they will eventually send that Soyuz craft back to Earth. Now, the thing is funny, is that they just had this coolant leak problem, and it turns out their cargo craft that had just gone up there and docked got a coolant leak too. So that's the second time it's happened this year. Really kind of surprising. Luckily, it happened just before they're about to undock anyway. It was already loaded up with trash. Those cargo craft do not return to Earth. They just vaporize in the atmosphere. You're breathing parts of it right now. That's already been replaced, and it's been ejected in Progress 83, which is the latest cargo craft. That's there, which again, in the bigger picture, you can kind of see where there's the Russian half of the station down here on the right-hand side, where you have the manned craft like the Soyuz, and you have the cargo craft. And then the left-hand side of this picture is where you have the American side of it, the Western side. Okay, some other problems with the orbits. The space station, they had to raise the orbit again. This time, they were avoiding an Argentinian commercial satellite. Everybody has satellites up there these days. They don't all launch them themselves, but they contract it out. This is the 33rd time they've had maneuver the space station, including twice in 2022. Now, at least one of those, and maybe both in 2022, were because of avoiding debris from a Russian anti-satellite test. I forget if the other one was as well. But in any case, it's happened fairly often throughout the history, and it's likely to get a lot worse. That's actually the point of this graph that you see down here in the lower right corner of the slide, where there's a lot of objects that are tracked. In this case, the objects that are greater than 10 centimeters. So that gives you an idea of the size they're tracking.
About 4 inches.
Yeah. And this is plotted as a function of the year. And of course, what's interesting here is notice the active objects, meaning satellites typically, that's just shooting up exponentially right now. And it's going to go catch up even above the total, today's total, fairly quickly, just because of all the satellite constellations going up, like Starlink. The Chinese are going to put up one. there's OneWeb. There's just so many of them out there now. The net result is there's just a lot of crowding up there. There's a lot of chances that things are going to happen. So what are we going to do about it? Well, there's been a lot of proposals, but not much has really been done yet. Part of the problem is that most of the satellites actually are up higher, even the ones in low Earth orbit. Most of them are up higher than the space station. So what happens is over time, their orbits decay. There's still a few particles of air here and there. That's enough to slow it down. The orbits gradually decay, and then they come down, and they encroach in the area of fairly sensitive ones, and big ones like the space station. So the ideal would be when you reach the end of the life of your satellite, they have propellant that they normally use to continually put themselves back up in a higher orbit, but eventually that runs out. And when that runs out, that's when the danger is. So what they'd like people to do is when they deorbit, do it fast. Basically, slow down a whole lot, come crashing down through that lower layer, and then get into the atmosphere and burn up. So that's the goal. There isn't much to make that happen yet. Now, a lot of the big commercial operators they can do this. That's not too much of a problem. Starlink, for instance, that's part of the normal plan. But a lot of older satellites, they've been up there a while, and they may not have this. Now, that's interesting because we're talking about here the satellites that have propellant. Not all satellites have propellant. A lot of the really small ones, the CubeSats, they may have some, they may not, but they have other means of also slowing themselves down. One they just tested out, I think it was last year, and this might have been a European test. They basically tested just sticking out a little antenna-like thing when they get to the end. And just that extra bit of air friction is enough to slow it down faster so that it'll, maybe within a couple of weeks to a few months, it'll end up coming in and getting out of that danger zone. And there's another one, the satellites that were put up by this company called Swarm that was actually bought by SpaceX. They do Internet of Things communications with small things. They're the ones that have the ham sandwich-sized satellites, and they're flat. And so visualize, if you're trying to stay in orbit as long as you can, you have the narrow edge facing the direction you're going, so you're not hitting too many air particles. When you want to slow down, you reorient yourself, but they don't have thrusters. But what they do is they turn on magnets, essentially, and they line up with the Earth's magnetic field. They take advantage of the fact that there is magnetism in the field, and over time, that doesn't happen instantly, but they can turn themselves. And once they turn themselves, and then the flat side is hitting a whole lot more air molecules, again, they come down faster. So there's a lot of ways to address how do you deorbit quickly, but it's a problem that really has to be solved. Okay, some other miscellaneous news here. Rocket Lab, they're the ones, the small rocket launcher that started in New Zealand, and now they're in the US. They didn't initially recover their boosters, and that's really been proven to be economically essential. If you want to compete in space, you pretty much have to be able to reuse your equipment. And so what they did is they were going to recovery by nets, having a helicopter catch them in a net. And they almost got it one time. They got it in the net and they dropped it. And the last time they tried it, it didn't work at all. But actually, luckily, they re-examined what they had that dropped into sea, and it turned out, actually, it's okay. So they decided the sea recovery is good enough. They're officially giving up on trying to recover their boosters with a net. And what they'll focus on is making sure that anything that's sensitive to corrosion, that they will beef that up a little bit, change the metallurgy, whatever they need to do, and maybe also put a little bit extra flotation devices just to keep things from getting so wet. So that was another solution, which isn't that different than what they're talking about doing for the Vulcan, which is a bigger rocket, by United Launch Alliance. So there are alternatives to what SpaceX is doing. You may not get quite all the benefit, but you can get quite a bit of it. Next topic, there's several Mars rovers up there. We have two, Curiosity and Perseverance. The Chinese had put one up last year, and it had worked, it was working quite well, but it looks like it didn't survive the winter in the northern hemisphere of Mars. What happens there is, just like on Earth, you get colder, it's darker more often, and also on Mars, it turns out you get a lot of dust. For whatever reason, the atmosphere conditions favor having a lot of dust. And that craft was solar powered. Unlike the American rovers, which are nuclear powered, they don't have that problem. They don't really care that much about the temperature or the light. But when you have a lot of dust, it builds up in the solar cells. That killed the U.S. InSight lander, which was not a rover. It was just a lander. That was the one that did the seismic analysis and that sort of thing. So things that are solar powered, they do tend to have problems on Mars. There's less light to begin with, and they're sensitive to dust. It looks like that probably took its toll with the Chinese rover. And then I'll get into the main topic here. Blue Origin made kind of a surprise announcement. I don't think many people knew this was coming. They just announced kind of quietly saying they can build solar panels on the moon, and meaning they have a technology they think they can do it with. They've done the process on Earth. Obviously, they need to test it in space to make sure it works in low gravity. test it on the moon to make sure it works with their conditions. But the key thing is they could build them just using the regolith, which is dirt. You don't call it soil, because the soil tends to imply you have microbes and stuff, which you don't have. Just regolith. And that's an example of using in situ resource utilization, living off the land. And ultimately, something we really have to do well if we're going to get to space and live there in any quantity. If we want to have many people there, you can't just supply everything from Earth. So one of the keys to settling the rest of the universe is living off the land, and this is a start. Making solar cells, turns out, that's actually an old idea, going back to, well, at least the 90s, when people started worrying about silicon chips and that sort of thing, and realizing, oh, you got all those things in the crust. But let's talk briefly about why you want to do this. Here's an example. This is a typical picture. This was out of the European Space Agency, kind of a vision of a moon base. And, yeah, it looks pretty cool. You got some people there, you got some solar power, you're growing some stuff. But one thing that's basically wrong with this picture is that, well, it's inevitable you'll start off like this, but the question is, can you stay like this? Basically, everything you see in this picture came from Earth. Now, the one exception, they made some use of local materials. They did bury the habitats a bit with the regolith. You can see that in the upper right side there. They bury that habitat and part of the one next to it. And that's actually like the simplest possible in situ resource utilization. You can't get simpler than that, but it's actually essential. For one thing, it provides an insulating layer. It gets very, very hot and very, very cold, depending on whether you're in the light or at night on the moon. And the other thing is you need it for radiation protection. You need both of those things. And so that's the one thing they're doing there. Their uses that. Now, the other thing that maybe they've done a little bit of local utilization is you can't really tell what's going on in that little agricultural area there. Maybe it's all hydroponic. It looks like maybe not. So maybe they figured out, some way to use the regolith as dirt, so you don't have to bring all the dirt from Earth as well. You can't tell in this picture. But still, the fundamental problem is, this is great. This is sort of the Antarctica model. Basically the South Pole station. It's out there by itself. It depends completely on resupply from the rest of Earth. And that's kind of how the space agencies around the world have traditionally viewed going to space. They imagine setting up a little research post somewhere that has to be supplied 100%, from Earth. We'll never get a significant number of people in space if that is the only part of the model. So the real question is, how do you scale up something like this? If you want to put in twice as many people, you got to ship twice as much stuff. And then you've also got to maintain it with parts from Earth on the long term. You have to replace those solar cells eventually. So that's why people have talked about making solar cells on the moon. It's attractive because we know the ingredients are there. Everything you need is there. You got 20% silicon in the typical regolith. 10% of it's aluminum. So silicon you need for silicon-based chips of all types, whether any kind of semiconductor, whether it's solar cells or whether it's a CPU. The aluminum you can use for structural use, and of course you can also use it for wiring. So you got pretty much everything you need just right there. It's mostly tied up with oxygen. 40 to 45% of the crust is oxygen, meaning silicon dioxide, aluminum oxide, and then there's smaller amounts of iron, titanium, a variety of other rare earth kind of metals. All those things are there. So those things can be used. And what Blue Origin came up with is they're saying they can actually do it. Now, we talked about why you might want to put solar cells on the moon and have them built there. Obviously, you can increase your moon population much more easily if you can source it locally, at least get your energy supplied that way. That's half of it. But the other part that excites people is this may be a cheaper way to get space-based solar power. There's a picture here that this is actually from a Japanese proposal for a particular way of doing it, but they're all pretty much the same in that the sun illuminates basically a whole array of solar cells. They may be connected like this, they may not be, but one way or another, you're illuminating a whole area of them. Typically, you have a panel with some electronics in the middle, and on the backside of that, you re-radiate that as microwave radiation, and you focus it, back to Earth, or you could do it for Mars, for that matter, or on the moon. But anyway, the main thing is you focus it somewhere else. And the reason you want to do that is it costs a lot less to launch something from the moon than it does from Earth. The gravity is only 1/6. So you can get a lot more solar cells up there if you can make them in some reasonable way. Anything you can make on the moon, if you're going to use it in space, it makes sense to source it from the moon or asteroids or somewhere else. But the main thing is don't try to source it from Earth. That's just a whole lot more expensive. So the hope is maybe that'll lower the costs for a space-based solar power. So their announcement, they had a process they called Blue Alchemist. which allows manufacturing of a complete solar panels, not just the cells, but also the glass that covers them, protects them, and the wiring. And it is made, they've tested it with a simulant, meaning something that's very much like the Lunar Regolith. And they've done it since 2021. They say they've been doing this for a year now. And the technology is called Molten Regolith Electrolysis. And what it does is it basically frees that oxygen. You know, we said we have iron oxide, silicon dioxide, and so on. If you heat it up really hot, about 1600 centigrade, which is like a little less than 3000 degrees Fahrenheit, it melts. And if you pass electricity through it, that actually breaks that bonds to the oxygen. And as a result, you can pull out iron, you can pull out silicon, and so on. They're saying they can make silicon that's 99.999% pure. So, you know, that's what you need if you're making semiconductors. There's a certain amount of doping material you have to add in there, and I'm not sure if they have to import that or they can also find that in there. But fundamentally, almost all of the mass you're looking at, they can get. And interestingly, there's no water involved, there's no toxic chemicals or carbon emissions, unlike on Earth, where actually all those things are needed quite heavily. And anyway, this includes the solar cells, it includes the glass that protects it so they can last maybe 10 years, and all the wiring. So that's really in situ resource utilization kind of at its best. Now that's the good news. And the bad news is they provided no details whatsoever. How much power does it take to do the mining? What are the economics of the whole thing? What are the details of the process? We don't know. On the other hand, just the fact that they said it's molten regolith electrolysis, we do actually know quite a bit about that because that's been studied for a while, and I'll get to that later. But the key thing is this has just been done, and it was done independently. NASA didn't, or anybody else. Nobody else funded this. They just did this on their own. Now they're going to go back and try to get funding from NASA to start integrating it into the various space programs. That's their hope. So then that's when, we'll see, well, does it really work? First of all, you probably try to do it at least up on the space station because that's relatively easy to get to. And then at some point, you would try to do it on the moon as well. So let's talk about scaling up. We were saying before, if you want to have more people out there, you need processes that can use local resources. So think about the way this process works. If you have all those solar panels available, you make some more, then you can generate more electrical power, then you could manufacture more solar panels, and the whole thing goes in kind of a cycle. And so, the question is, will you be able to just end up covering the whole moon in solar cells? Well, no, not necessarily. But it does raise the question of you essentially want to look for this, call it a virtuous cycle, if you like, is positive feedback. Once you get it started, the trick is getting it started. And it's a trick because you have to get all that equipment there in the first place. You also have to have enough spare energy available to do the initial melting and getting the manufacturing process going. And of course, probably people to help set it up. So really the limiting factors on this process for just reproducing itself over and over again are, one, the equipment itself. Right now, that would have to come from Earth. And the other thing is, of course, you're going to have human effort in setting it up and probably for maintenance. Nothing stays automated and runs remotely forever. So you need something. So as a result, it's not really likely to be exponential growth because you have these other factors where you still have to bring in from Earth. But it's getting pretty close until you can start manufacturing the equipment itself on the moon. And if you can automate most of the operation, then you're approaching that. And you can generalize this. In general, if you're going to expand into the solar system with people, essentially entire settlements have to replicate themselves. And it's been one of those questions that people have had for a while. How many people, and how much technology is needed that you can actually exist pretty much on your own? And then, of course, that also applies once you figure that out, once you have kind of a settlement in the box, then you can start reproducing that in other places. And that would certainly be the goal. Short term, that's not going to happen. You obviously would never build things that big anyway, but this was just sort of a conceptual slide. Talking about the in situ resource utilization, living off the land. As I said, really, settling space is about cost. And SpaceX has gone a long way in reducing cost to get to space. Starship, when that really finally works, they're going to reduce cost quite a bit. That was a necessary condition to actually settle space. But it's not sufficient. You also had to be able to figure out how to live off the land, because even with cheaper launch costs, it's still going to be pretty expensive. You got to minimize dependence on Earth if you're on the moon or Mars or near asteroids anywhere. And that will enable, expansion into space. So we've talked about a lot of these other examples in the past. Getting oxygen out of the Martian atmosphere. That was a test that was done on the Perseverance rover, just because that was there. That was about the only shot at getting it. So they proved that they can do that. There's a possibility there. The atmosphere is carbon dioxide almost exclusively. You can break the bonds of that carbon and oxygen and pull out the oxygen. We talked last month about mining asteroids. And actually, we talked earlier about some lunar processes as well for doing that. Other examples, taking water. There are deep craters at the lunar South Pole that probably have water ice in them. There's enough evidence that you can actually get that relatively easily. And of course, you obviously need it for drinking, but also you can electrolyze that to make oxygen, and you can react it further. Well, you can use the oxygen as propellant in a rocket, and you can react it further for other chemicals. Even at a more basic level, just paving, building structures, and protection from radiation. That's an obvious use of in situ resource utilization. Those are probably the first things that would be done. And yet, to make a side comment, the main manned space programs don't even plan for that yet. It's almost like there's two parts to NASA. There's the part that does the big showy projects, like getting people to the moon and then on to Mars. But they don't actually use any of this stuff. They're just kind of assuming the Antarctic outpost kind of a model. And then there's all these other research that NASA is funding for doing all this other kind of stuff, the ISRU, which ultimately is going to be a lot more important than the showpiece, get an astronaut to Mars kind of thing. Well, agriculture was one more example, just turning regolith into usable soil. So how do we do the regolith electrolysis? What the heck is that? This is what Blue Origin is using, and it turns out there's another Houston company that is actually doing this too. It's a variation on something called molten salt electrolysis. It's been around for 100 years, and it's used for aluminum, magnesium, and rare earth metals. Not all of it, but it is a significant process in all of these. The idea is, in their case, you have molten salt, meaning it has to be pretty hot to be molten in the first place, and you pass electrical current through a bunch of ore that is submerged in that salt. And the electricity, just like we're talking about with Blue Origin, it breaks down the oxygen bonds to the metals. And one way or another, you end up pulling out the metal. So the Earth applications, of course, they don't care about the fact that you're freeing up oxygen. That just goes out to the atmosphere. Or worse, actually, because they use anodes and cathodes, the anodes that they use are made of carbon. And actually, they end up generating CO2. So actually, it's kind of bad that way. This has been studied. This process has been studied for use that way. The European Space Agency, for some reason, went into that approach. And they're looking at using calcium chloride as the salt on the moon. But on the other hand, NASA kind of went a different direction, basically inspired by some MIT research back in the 1990s. Someone just said, just melt the regolith and use that as the electrolyte. Don't bother with having salt or any of that other stuff. You don't actually need it. Now, the reactor has to be specially designed to handle this. It has to be kind of self-heating, meaning you pass the electrical current through it, and the heat from that in the electrolysis, that in itself is enough. Once the reaction is started, it just keeps on going. But the other issue is, how do you contain something that's 3,000 degrees Fahrenheit? Your average material is not going to hold that. This is something they are borrowing from the aluminum industry. You simply use the ore itself as the outer material, the refractory material, which protects everything else from the heat. You start heating stuff up, out at the outer edges, it ends up refreezing, and solidifying, and that pretty much is your wall. And so it's actually easy to contain that way. So what are the technical challenges with this process, though? First thing is that regolith is very high resistance, and that's true even when it's molten. So for instance, it's a lot worse when it's cold. I mean, if you take your average rock, you try plugging it into the wall, you take some wires out of the wall and you try to short out those wires with a rock. You're not going to heat that rock up because the resistance is too high. You won't get enough current going through it to do anything. So starting the whole process up, that's tricky. So the cold start says you have to have a lot of energy there to get the whole process going, to get it hot enough in the first place. Then, of course, the molten material is a problem. What do you do with it once you got it? Now, this diagram here shows, on the right-hand side here, shows the way things work. You got electrodes basically at the top and the bottom. Think of this thing as a cylinder with a big plate on the top and a big plate on the bottom. And one end of it, you get oxygen coming off. In this case, it's at the top on the anode. The other end, you're getting the oxygen out of the iron or silicon in this case, and so it's falling to the bottom. So you have essentially liquid metal down here. So you got to figure out how to get it out. And that actually, I've looked through just skimming, some of the papers that have come out on this stuff. That turns out that's a tricky step. How do you do that? You could do it as a batch. You can heat the whole thing up and then just let it all cool back down. That's incredibly inefficient from an energy standpoint. You put all that energy into heating stuff up and then cooling it back off. But everything has been done pretty much in a lab scale on this molten regolith technique. So that's still a problem for them. You'd want to have some kind of a pipe or something to let the liquid metal come out, but what do you make that pipe out of? They're still working on that. That's sort of not really completely solved problem. And that's why you wonder, well, what is Blue Origin doing? They apparently are claiming they've solved some of this stuff. So yeah, life of the electrode is an issue. Separating the products. In the case of most of the other processes for aluminum and so on, they use salts that specifically absorb what they want, like aluminum. Here you're going to end up getting iron and silicon and everything else. You got to separate that stuff somehow, and nobody says how they're doing that. It's really not very clear. And then, as I mentioned, batch processes not very efficient. They want to do continuously. Again, not clear. So there's a lot unknown really about what Blue Origin is saying. But they're not the only company doing this. There's a company called Lunar Resources. They're here in Houston. They're also doing this, and they are going out maybe in 2024. They are sending a prototype reactor to the moon. And its goal is basically metal extraction, iron, aluminum, magnesium. They've done this with private capital and with funding from the National Science Foundation and NASA. So they've gotten funding for this. As I said, 2024 is their goal. This thing you're looking at here, what they call the reactor, which is where the reactions would occur, is about a meter, 3 feet diameter and height. And what they would do is they would collect the regolith with a small rover. Their goal is to process maybe 100 kilograms in 24 hours. To do that, what has to get delivered to the moon is about half a ton. And they think the Griffin lander, which is one of the moon lander companies that's working on this, they've been working with them, and this is their vision of what it's going to look like. So you have the Griffin lander. That's a general purpose thing for getting stuff down to the moon softly. And then they're expecting a rover to move the regolith around. NASA is apparently providing that with some other project they're doing. The excavation and the truck, they're two separate devices, but apparently NASA is doing these with some other companies along the way. But what you're looking at in the center of this picture then is their processing units. And what's amazing to me is they have some solar cells there. That doesn't look like a whole lot, but they're going to get, apparently they're doing, only a small amount of work. Remains to be seen, but at least they're testing this whole thing out. So typically each time we talk about how much have we actually gone to space in the last month? What's actually attempted? Failures count. And if they tried to go into orbit, that counts.
15,000.
You keep coming down. You're getting closer and closer all the time. Okay. Well, it turns out, it turns out that the answer is 12, not counting that Terran one. And it actually looks a lot like it typically does each time. Maybe not quite as many as we had the last few months. It all fit on one page this time. Typically, there's a lot of Starlink launches, the internet service from SpaceX. There were some big satellites that went up, also launched on Falcon 9s. And of course, the Chinese have a variety of launches. Theirs are communications and Earth observation satellites. I will highlight the Starlink ones. They've been launching the same, essentially, their initial satellites, had a certain capacity. They decided to upgrade them to version 1.5, somewhere along the line. But they have a version 2 coming up, which is like 4 times heavier, 4 times the solar array size, 4 times the power and everything. But they won't fit very many of those on a Falcon 9, so they're not even attempting that. But they want to make progress. So what they've done instead is they came up with a version 2 mini version. And that will fit. They can launch like 21, and they did the first launch of that type, so they're moving along. We got some crew to the International Space Station.
Those satellites are probably the ones that they intended originally to launch from Starship, which they had planned on flying 5-6 months ago.
That's right. Yeah, originally those all should have been on Starship. The Starship isn't there, so they said, okay, we better get Plan B going here. So. And Starlink, at this point, they have about 4,000 they've launched. Now, there aren't that many of them actually up there because they did a lot of prototyping and that sort of thing. So, they're not all up there, but, probably 3,600 probably are, which is, more than existed before they started back in 2019. Now, Japan, in the form of Mitsubishi Heavy Industries, they had a new rocket called the H3. This was their first shot at a brand new rocket. It failed. That was actually the second stage failed. The first stage worked fine, but the second stage didn't. This is interesting because it's not really clear there's any commercial place for the H3 rocket. It's still going to be more expensive than a Falcon 9. Like, how many people are really going to want it other than the Japanese, who, of course, just want to keep perfecting their own rocket technology? It's not a reusable rocket, so it's never going to be completely competitive. And that's true with actually including the Terran 1. That's true for almost everything else is up there. Everything else, everybody's sending up rockets that are supposed to compete with the Falcon 9, which came out 10 years ago. Yeah.
Yeah, the Japanese have historically had a problem with their H1 and H2 and all their other rocket programs being not competitive. And there's probably something about the way they do business about being really, really very, very careful. I think they're a risk averse more risk averse than other countries. So consequently, they end up with things that are very, very expensive and market competitive.
Okay, and then the Chinese, they've launched a couple satellites too. So that pretty much covers it. And the end of my presentation. Any other comments or questions? Yeah.
I was at ISDC some years ago talking to the scientist, Dr. Robert Forward, and he was telling me about a way to deorbit satellites where you basically just unspool a thin conductive wire. At the end of the life of the satellite, you unspool this long, thin wire that'll be a couple 100 feet long, very fine wire, and as that wire, as the satellite goes through an orbit around the Earth, it cuts through the Earth's electromagnetic field lines, and that causes current to flow. And in addition to just the plain mechanical drag of the wire, this generation of electricity also causes the satellite to deorbit more quickly, with the bonus that it gets some extra, a couple amps of electricity to use for final tasks that need to be done before deorbiting. And Dr. Forward actually was a sort of a partner with another some folks who were doing that out there in Pasadena or some other place in California. But they were trying to get the U.S. Congress to pass a law saying that, and this was like 15 years ago, that if you launch a satellite, you will be required by law to have a means of deorbiting the satellite in a tidy fashion.
And I think the U.S. does that. I mean, that's part of the requirements now.
Did that? They didn't. I don't think they ever actually passed the law, but they did start doing it as a best practice. And now the next hurdle is to get the international community all to agree with doing that. And there are varying degrees of resistance to tidying up one's mess.
Yeah. Well, yeah, the Chinese are the worst at that. They leave whole first stages up there. But